Hello to viewers, welcome to my channel Science to Technology. In today's show, Computer Wednesday, we're going to talk about Sony's true RGB TV tech. Let's dive deep into it. So we have to understand what is the problem here. Problem is S-curve. Every technology goes through this S-curve, meaning you reach a point where it's mature, you can't really spend too much more money and get something good out of it. Like it has reached saturation, so to say. So for TV display, 4K is that saturation point. Like there is a massive jump going from SD standard video to HD. That's like, whoa. HD to 4K is like little bit improvement. 4K to 8K is like, meh. It does not matter, like flat out. Like you have to show people like this is the difference. It's like, yeah, no, like again, S-curve, it's reaching that point. Your eyes are like, bro, I can't tell. And most of the time people are saying, no, you can see this and that. Most of them, they are talking about compression artifact, meaning if you look at like, oh, Canon has this 8K camera, it looks so good. Yeah, what you are seeing, you can get the same quality out of a 4K camera and 4K display as long as it's uncompressed. 8K just has a better compression system because again, more pixels, more compression and headroom. And I can easily assume by AV1 codecs upgrades they will do that, even that problem would be solved. It's not even a problem. It's like, yeah, you have a bigger file, more data, duh. So we have reached that S-curve. You can't increase the resolution too much. I mean, like, of course, I do expect it by 2040, 8K becomes a normal thing just out of boredom, but it's not necessary. Meaning there was a massive jump going from SD to HD. HD to 4K is like, meh. 4K to 8K would be like, did it happen? Like, nobody would pay attention to it. So that's the whole point. Another is FPS. There was a time where it's like, what if we need more FPS? Like this monitor, that's like 4K, 120 FPS. Here's the, can you go higher than this? Of course you can do. But here's the, is there a difference? Like, does it make a difference? Of course it does make a difference. It's just that you have to be like ultra pro gamer in order to like actually complain that you are not getting more than 180 frames per second or 120 frames per second. Like for most people, it's like, we good, sir. Like 15 FPS, choppy. Anything above 24 is good. Now, why 24 is cinematic? Every time people say, no, cinematic, that's 24 frames per second. There were some people who did try to smoke something and they were like, what if we had 48 frames per second? Yeah, it was poo-poo. So we learned it the hard way. You do not want high FPS. Like you could shoot your car in 120 FPS. Why would you? Heck, people have like tried that 60 FPS and then they're like, yeah, let's just go to 24. It's far better, far more pleasing at 24. So yeah, we can go again, same S-curve, we reached that point. Like this display, again, assuming that the pixels were not burnt, is good. Like we good. So we reached a point where we can't increase the resolution, can't increase the FPS, but we do need a room to improve so we can grow. Well, that room to improvement is color. Color is something that you can almost average Joe can tell a difference between HDR content and SDR content, basically, and specifically if it's a true HDR, as in jumping from 8-bit to 10-bit, assuming the panel can render it. So right now, when you say 8-bit panel, that panel, each pixel can go on and off between like full on would be lesser 255 and off would be 0. So it has 256 levels. That will be classified as 8-bit panel. 10-bit was also there, but it was idiotically expensive. I'm pretty sure it's been there for 10 to 15 years, but it's very expensive. And I'm only sure that because of OLED, you are directly driving the system, it's actually a bit easier to do. So OLED does come with a 10-bit panel, although the control circuit may not digest it. It's a whole mess. Obfuscation of that technology is weird. But again, you have that option. The wiggle room is there. HDR supposed to utilize that 10-bit. Same 4K, same what you call 4:2 color space and all that, but you still have 10-bit. Oh, be mindful, do not confuse those 4:2 or 4:0 with this 8-bit or 10-bit. Those are two different things. One is compression, another is bit depth. So the jump between colors going from like, barely 16 million colors to billion color, that's huge jump. So, and again, it does show up to your eyes, meaning if you have a true color rendition, and this is just the mathematical part, let that be figured, that's just mathematics. But if you have a panel that can truly render it, it looks good. It's like good. So that's the window, that's the wiggle room. Like we have reached maturity in all other things. Like if you can make a panel that is 4K, if you can make a panel that is 10-bit actual pixel quality, and you can have like 60 FPS or 120, you good. Like you good. You can take care of most people from now onwards. However, color depth, that's a big difference. That's where everybody is fighting right now. So what are our options? Well, our options is OLED, one of the best technology. And again, that's why I paid kidney for this, LG CX 55-inch. So it's the best. And again, your mobile phone has it, your TV has it. And the biggest advantage is the black is not gray, the black is black. So it's super duper black. And benefit of that is sharpness. Look, even though it's 4K, it just feels sharper. Why? Because the black is black. It's fun. It's almost like, if you know comics generally have color first, then they do inking. They basically add a black outline from a very sharp point pen. So it looks like it pops. So same thing happens with OLED. And response time, ooh la la, there is no physical change. There is nothing, no crystals dancing. So response time is fundamentally, under the laws of physics, rapid. Meaning as long as your electrical circuit, as in your capacitor and MOSFET can switch, this puppy is like, I got you fam. So 120 FPS on these puppies are like crisp. Like I really wish that NVIDIA maintained its technology of that, like, having a shutter glass that can sync with OLED. It would be mind-boggling. You can easily watch 3D in your home. And again, it will not require polarizer or anything. It will be just like, hey, 130 FPS, shutter each of them at 60 FPS. So, and again, because it does not have that smeariness, it's truly crystal clear. But unfortunately, OLED was too early stage that time when NVIDIA was selling that, and it died off. So I never got that true 3D in home. Only few people, very few people got that. Like OLED with a proper, shuttering system, it would have been awesome. So each pixel is there, on-off is sharp, but it burns out. Already starting to burn out. Like being this close, I'm like, oh yeah, your pixel died, here, oh damn, I do not want to look this close. It's just like too many pixels died. So it does not last very long. That's the penalty. And it does not go bright. Now brightness does not feel painful to you simply because the black goes so black that it's like fine. In indoor, if you have a window pouring light into it, this is like, nope, this just becomes nope. In enclosed environment where you do not have sunlight falling onto it, great. Outdoor, don't even talk about this. This is useless. So that's the penalty of it. It does not last long and does not get bright. And that's a physical limitation. If you overdrive them, they will not last long enough. And even if you are conserving it, they will not last long. They're like, just won't last long. So it's, again, organic chemistry. However, somebody is like, hey, what if we use this puppy as in micro LED, as in the LED itself is there, like full-fledged inorganic alkali. Generally, they are targeting, instead of hydrocarbon systems, they are targeting gallium. So that puppy can handle that power. And that's the future, let it be very clear. We know this is the technology. Everybody has been working on it. It's just taking much longer. It's like, it's been there, done that, sorted. We started with the dots in place, like big LEDs. And you're like, did anybody use that? Yes. This was like back in the days, like Lincoln Park days, stage backlights were made out of this. Then it became surface mounted. Then it became integrated matrix pixel. Now, currently, we are co-op systems and people are working on micro LED. Basically, size shrinking. Everything else is sorted. Electronics, physical panel, all of those are sorted. We just have to keep making them smaller. Small enough that I can be this close to it and still do not see each pixel. So that's the hard part. Again, can it be done? Yes, it has been done. It's just that yield is not stable enough. So fundamentally, it will be the future because that will have the best of everything. The quality of OLED while having the brightness of LED and lifespan of a LCD. Actually, more than LCD. So that's there. And these things are so powerful, they can directly stare at the sun and be like, bro, you can still see me. Like brightness on these things are crazy. Like 5,000 nits is like, bruh, I don't wake me up. Like power supply will be like, bro, like you watching under like what? So sunlight visible, long lived. These things are solid, robust. We just have to miniaturize it more. So alternatives is there. The technology has been sorted. OLED was just a, what you call, bridge technology. So we come to LCD. Now LCD is the most common display type. As long as you are not directly looking at your mobile phone, smartphone, tablet or those sort of things, 99.99% of the time you are looking at a LCD. Now LCD has a white light, then it has color filter, then it has pixel. Pixel is the part that turns on and off. Now, technically, pixel and subpixel is a different thing. Whenever you're talking about pixel, you are talking about something that can be RGB. But when you're talking about from a monitor, it has subpixel, meaning if you take a magnifying glass, look into it, it has red, blue, green, independent pixels that computer knows, a computer as in like the driver circuit knows. And when you are saying make this pixel red, it's disabling 2 subpixels and making the red pixel full. So that's why color filter is before the pixel. So white light, color filter, pixels, and polarizer. Now it has bonkers amounts of loss of light. For example, if the backlight is pumping out 100 watt, you might be getting as low as 10 watt out. And that's the physics of this puppy. As in your light, white light, it's chaotic. It has broad spectrum, as in it has everything. And if you know anything about filters, filters are not perfect. Nothing is perfect. So you have a lot of bleed through, cross through, meaning a green filter, it has a little bit of magenta leaking it, little bit of this, little bit of that. So it's messy. And to handle that, we have polarizer. Polarizer polarizes everything. So that itself is the biggest waster of energy, meaning most of your photons are lost there. Then because we have polarizer, the on-off circuit, as in the crystal, because it's polarizer, it's like this, light goes through. If it's like this, nope. So that's how you do it. And to make sure that it actually translates to it, you have another polarizer. So you have horizontal and vertical polarizer, and inside that you have the pixel going on and off. So it does work. It does allow you to pixel to go from 0 to 100%. That's why the polarizer are important. But again, as you can see, it's a physical crystal that is physically rotating. And not only rotating, it also has to have the ability to rotate like little bit, and that little bit, again, 256 bits, 256 stages, 1084 stages. That's the brightness control of per pixel. Again, in OLED, it's super easy. It's just like PWM and voltage control the LED, done. It's like even ESP32 can do that. Like again, pixel level I'm talking. So these sort of things, and again, whenever you talk about people say LCDs are smeary compared to OLED, that's the reason. This takes time, like it's a physical thing, it takes time to switch. So after that polarizer, you get the full output. So most of the light is lost. And again, without polarizer, it will not work. So you have to have that. And again, you must have seen people say, what if they remove the polarizer, it becomes white, and you wear the polarizer in your glass. It's like, why is that white? You already had one loss of light, second did not happen. That's why it's so bright. So it does work. It's a good tested technology, but black is not black, because even though we are losing so much of it, filters are not 100% perfect. This crystal unit is not 100% perfect, meaning off is just suggestion. Photons leaks through it is just like, okay, it's not off. So photons are leaking through it. So it does not work that well. And so you lose both sides. Basically, for brightness, you have to over brighten it, and that creates a paradox where it's like your black becomes gray. So some people figured out compound interest, as in if one crystal unit can, let's just say, have only 90% efficiency, what if from its output you have another crystal unit that does another 90%? Now you have 99.9% efficiency, as in like control efficiency. So this was the trend in professional pro grade, as in like don't ask me the price kind of people. They always had LCD that had a LCD behind it. Sometimes it was not a colored LCD, it was just a what you call luminance LCD, and they had a like full YOLO super duper hyper bright LEDs pumping light. First there was a layer that filtered it out, then second layer filtered the more out of it, and the contrast was GG. The quality was like good. I've linked a DIY Pox video. He tried to make it and it was good actually. So it is a real thing. You can have two systems, but again, it never peaked into what you call popularity, because again, expensive AF, and your LCD is now hot. Like instead of energy saving, it's hot. So it does come with some side effect. Second was the more logical approach is like, hey, use this as a high filter, high frequency filter. Use the backlight as a low frequency filter. Meaning, if these areas are black, why do you have backlight there? What if you turn it off? Now, back in the days, as in like 1990s, you could not have done compute enough for this. Nowadays, it's a trivial. So it's like, okay, take the video signal, calculate the lumens component out of it, draw the pixels on the LED backlight, and tada, turn off the LED where it does not need it. So this is the second option. So double LCD is not the future. This is the future. However, early results were crappy simply because they only had few pixels. Like 5 to 6 pixels, 6 pixels, like they needed a lot more pixels. So nowadays you have like 200, 300. If numbers are that small, yeah, don't pay attention to it. It's not that useful. It has the worst output of when you are moving a black background, mouse pointer, white color, it will have a worst halo because each backlight element is supposed to illuminate lots of pixel, lots of, like almost like a centimeter square pixel surface area, so to say. So we used a quality LCD does have that advantage. That's why it was used in cinema. Color grading, like cinema critical work, they will always use that because this, But nowadays we have enough technology, enough LEDs, small enough LEDs that this can be handled. So this is LCD. And again, remember this, like this filter is the worst problem that you have to deal with. So Sony RGB took page out of quantum LED. So the idea is liquid crystal is a physical limitation. You cannot bypass it. However, you can help it. For example, quantum dot was the biggest help. It was like, hey, what if behind your color filters, you have quantum dot? Now, why would you have that? Well, all the LEDs now are, instead of having white, it's just blue. So you take blue photons, goes through blue quantum dot, it's pure blue. What does pure blue means? Pure blue simply means white whenever you're looking the nanometers, right? So it's a range. Like sunlight, it's a huge range. Laser, it's a tiny range, very tiny, like very, very tiny, 4 nanometer, 5 nanometer. I'm like, how wide the bandwidth is. LED is not that monochromatic, but not that tight. So it's almost like this. So when you go through quantum dot tightens it up. That's why it looks so saturated, where it's like, whoa, because it's tight. Now here's the deal. A filter is very efficient in one wavelength. If you know that, let's just say this blue filter is like 300 nanometer and you design only 300 nanometer light going through it, it's like, I got this. I can block 100% of it. I can allow 100% of it. That's how efficient filter becomes at monochromatic light. So quantum dot takes blue light, makes it pure blue. And if it's like, okay, that's for blue pixel. What about green? It downshifts the photon, meaning it takes the high energy photons, dumps it into 2 smaller photons, which we call it green. And for red, it takes high energy blue photon, dumps it into bonkers amount of red photons. So you get crisp, precise. Basically, if you look at the output of the quantum dots, it's not white color. It's red, blue, green. Now, like, wouldn't that give a crappy output? No, it will give you perfect output because you do not want white light. You want video file. What is video file is storing? RGB. You only have that data. There is no reason for your backlight to have any component of yellow. There is no reason for that. There is no data for it. So RGB allows you to have that crispness. And again, filter become more efficient. And since filter is more efficient, the polarizer is also more efficient. And all these things allows your LCD to perform like it's almost like a double panel. Like quality is like, whoa, it's good. So quantum dot was the first thing, meaning what's the selling point? Monochromatic narrowband filter. So somebody came up with the idea, okay, why go through so much hassle? What if the backlight is the display? What if the backlight, instead of just being a backlight or white light or blue light like this, what if it was the display? It was a pre-display. Basically, we have the technology of LED wall. What if you just have the wall and the backlight? Problem solved. So you need to broadcast yellow, the backlight is yellow. You need red, backlight is red. Everything you need off, it is off. You need white, it is white. So that solved the problem. So that's what Sony figured out. Now here's the deal. You might be like, okay, how much resolution we are talking about? It's almost like going from 4K is the main filter layer. This could be as high as 720p. Like, again, they have not talked about it, but like it's very high resolution. That's the big difference between zone dimming and this. This is like almost like a low resolution display. Like, I'm pretty sure it's copy paste of this. Pretty sure of that. Again, they will have suppliers and contracts and all that, but it's pretty sure of that. And what Sony is saying that others are not doing it true. And again, blue LED is generally used for that, quantum dot. So this will have quantum dot that will allow you to pump it. But again, what's better than that? Have the L backlight as the pre-light, so to say. Basically, you're preloading the image, preloading the backlight, then this filters it and everything becomes awesome. Basically, like you have RO filter, another RO filter. So that's the Sony RGB technology. Basically, the backlight is this thing, low resolution LED wall. So what can we expect in the future? Micro LED is taking too long to mature. That's the only problem we are dealing with. I thought it would be ready by now. Like, I'm not joking. Like, I remembered, like when I was researching for this video, I was like, huh, I remember like Linus Tech Tips like 4 or 5 years ago is like, you know, this Samsung the wall, and it's like still has not come down in price, still has not, yield has not yielded. Basically, people figured out how to make the LED element, the gallium element, is just like bonding it to silicon substrate is proving too difficult. Basically the wire harness and all that. So micro LED is too long to mature. OLED does not last long enough. Again, talking from experience. Like again, I love the quality of it. Just hate the fact that I'm here and pixel. I hate that part. So that's it. LCD is a very mature technology. Like we good, we got this. Like we have fixed its angle. Again, polarizers were the reason why you had like such a crappy angle, viewing angle. All of those problems have been solved. And it's a long-lasting technology. Meaning compared to OLED, is like this puppy will last forever. And micro LED you can't buy it for your home, so LCD is like good. So most TV brands are realizing physics is same, all LCD is same, so they're like, what if we add RGB backlight to it? Basically a screen, like have a screen behind it, not have backlight, have a screen, low resolution, bright screen. So that's what they're doing, and that's the final form of LCD. I do not see any even theoretical things that they can do to LCD to do much more to this. Like again, the crystals have the inherent limitation. You can't do much more than that. So that's the final form, like improve the backlight itself. You can't have two LCD because that's stupendously expensive. Zone dimming is like not that good. This solves that problem. Quantum dot, again, quantum dot can be added to this to amp it up, but that's it. Again, you have RGB here, like literally RGB system. So fundamentally, it's the final form of LCD. It's reaching a point where unless fundamentally nobody can crack micro LED, I am pretty sure this will only last 5 to 10 years. Like final phase of like CRT TV, it's almost like final phase of LCD. We're gonna give up after this. Oh, something new can happen, but like my money is not on it. Now, what Sony is claiming is that there are companies that are bringing this technology right now in the market. By 2027, multiple companies would have brought it out. They are claiming they are true. That's the whole point. True RGB is simply because while the other companies do have RGB LED, as in like you open it up, see the LED, they are RGB LED. You run a test pattern, they are running at RGB system, meaning red, blue, green if you have that certain system. However, when you are running a video file, this does not do that because computational requirement is high, because again, now you're running a low resolution display behind it, and it's just not luminance anymore. It's not just white LEDs, it's full-fledged calculation, and you have to do some sort of tuning. Basically, you have to tune the algorithms so the bloom is minimized and color is maximized. So that does require a bit of compute horsepower, real time. And again, it's not that high in terms of compute, but if you have to make a mass production TV, you can't put a goddamn FPGA unit to do it. So that does require some silicon level mastery. So their analysis, Sony's analysis, is that there are companies that have the hardware, but they do not have the chip to drive the backlight properly. So whenever you are actually watching a movie, it's just becoming into a blue system, relying on the quantum dot to pump it up. And every time when people are testing it, they're using like cheating like Volvo did. So that's what Sony is saying. And this is from Sony's system. RGB LED, other companies also have that, but like Sony's advantage is the backlight control, and they did not even give a reference image for the IC. It's like XR, that's the main image processor, and then backlight has new IC. I'm pretty sure patent is not blocking it. Somebody might have patented 20 years ago and it has expired now, so that could also be the case. So again, they would not say Sony's advantage, they're like Sony's patented technology. Again, Sony did have Trinitron as a patented technology for quite some time. So this is the final form. Now, again, I would urge you, if you're thinking about buying this, be mindful. This would be painfully expensive because you are literally buying two displays. You're buying a goddamn LCD, which most likely have a quantum dot, and a full-fledged LED systems. Painfully expensive. So I would say wait for 2027 and hope to God somebody figures out micro LED. So this was my presentation on Sony's true RGB hulala. Hopefully you have liked it, learned from it. In that case, please hit the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching.